So welcome to BJT as an amplifier. So what I want to do is just bear with me. I want you to stick with me for about 15 minutes. There's a whole lecture here, but ultimately what this lecture is all about is that there's some theory you guys need to know, and I can cover that in just a few slides in a few minutes. The rest of this entire lecture is there's review for the first part, which you guys can go over yourself, or if you really want to review, you can go to last week's lecture and just watch BJT as a switch and wrap your head around that. So the next slides are essentially going to be some theory about how we use a BJT as an amplifier, which is in active mode. And then there's a bunch of math. There's a bunch of examples. And those examples, you can go through them yourself, but ultimately I'm walking through two different examples on the board, on my whiteboard in my lab. So, and those videos are posted under this week's lecture material. So what I'm saying is just stick with me for 15 minutes now while I go over some really basic theory here, which is just an addition of what we did last week. And then you can actually go and watch me do the math. So let's just run through these slides. So BJT is an amplifier as a switch. So this is review. I'm just going to go, this is where we're working in a cutoff or saturation, right? And you guys did the lab and you get all of this stuff, and you need to know this stuff because it's seriously on the exam. Like, I'm very serious about how much this is on the exam. Some applications, open, close switch, another application, turn stuff on, turn stuff off. And then some math on how to actually do it and do some calculations. So that's, that's just all review. Now, the meat of this lecture is BJT as an amplifier. So we're going to be working as opposed to, we're going to be working in active mode. Let me go back here. We're going to be working in active mode. And the application for amplifier is this. So we have a small input voltage, and our output voltage is going to be amplified. Over here, we have an input voltage that's an analog change, and we want to amplify that, and it's going to be an amplified value of whatever's coming in. Now, you can also put an AC signal in that has a low value and then put an AC signal out through a BJT, although we are not going to cover this. This is called a Class A amplifier. We are not going to cover this because you guys don't need to know how to amplify AC because it's not used in control systems. It's simply not used in control systems. Essentially, there's no reason why we're going to have, say, a sensor that's going to give us AC information. I mean, there are some sensors that give you AC, but they come with modules already that are already connected. You just connect them directly to a PLC. They give you an analog out. So we're not going to actually be using BJT as an amplifier for AC signals, but we will be using them for DC signals to create sensors and also to control devices like motors and solenoids and heaters and stuff, or output devices, lights, that we want to control in an analog fashion with sensors or very small voltage signals. So if I have a very small voltage signal and that signal is changing, right? It's coming from a sensor or even just a potentiometer. And I want to turn that into control. I want to use that signal to control an output that's going to be a high voltage and maybe higher current. I need a BJT. So I'm amplifying that lower voltage and that lower current signal to create a higher voltage and a higher current signal in an analog fashion. I'm not just turning things on and off, which is what we did last week for BJT as a switch. So we're working in this region here, okay, where we're not fully saturated, which means that we're going to be working underneath the current that saturates this. Now we know that if we take a look at the gain, and we know we calculate how much current I need to go through here. I divide that by the gain. Then I can calculate the amount of current I need to put through here to fully saturate this. But my question is, what happens if I put less current through than what I've calculated? If I calculated that I need 1 milliamp to fully saturate this, what happens if I put half a milliamp? What happens to the BJT if it's not fully saturated? Now remember, BJT is a switch. Open and close. Open and closed and open, right? What happens is it kind of opens a little bit or it closes just a little bit. It's kind of an in-between. It's like a throttle valve on a fluid power system, right? So you're throttling. You're essentially kind of slightly turning open and closed a valve to allow a certain amount of current going in and out. So we're controlling the current with current, right? But we're controlling it in an analog way, kind of, a little bit open, a little bit closed, all the way open, all the way closed, kind of in between there. So that's actually what's going on. So that's what we're doing. We're working in this mode. Again, if we calculate if this is, say, 100 milliamps when it's fully on, if it's 100 milliamps, then I know if my gain is 100, right? So I need 1 milliamp to go through here to fully close this switch and to get that thing to have 100 milliamps going through. But if I only put half the current through, I only put like, half a milliamp through, or 500 microamps, then there's only going to be half a milliamp, it's going to be 50 milliamps going through here. And this, whatever the load is, it's a light, it's a motor, it's a solenoid, but it'll be going at half. Pretty cool, or half the current. Not half the power though, because power is I squared times R. That gets complicated. Yeah, well, we studied that actually in ATM on 110, where we saw the power and the voltage and the power, the current, are not completely linear. The interaction is not linear. So let's pay attention to that if using a BJT to power something, say a motor, and you want the motor to go at half power. Well, you don't want to just divide the voltage by half. You have to do the math there, or the current by half. So there you go. So that's essentially what's going on. So yeah, we can use them, and we can use NPNs or PNPs. And what I'm going to do is I'm going to do next week, which we don't have class. I'm still going to post a video on a little bit more cleanup stuff that we would talk about next week. Not going to be specifically on the exam, but it's just information, difference between NPN and PNP, and how we actually build like a sensor circuit, calibrating with an amplifier. But it's just stuff you need to know. You don't have to watch it if you don't want, but I'll post it anyway. This is just an example here. This is interesting. This is kind of a new example here, where as opposed to turning something on and off, right? Like I'm not going to just have a load here, that I'm controlling the load and controlling the current through the load. What I'm going to do is I'm going to study the voltage of the collector, and I'm going to call that my voltage output. And as I change the current going through the base, as I vary the current going through the base, my BJT is going to be open a little bit more or closed a little bit more. What's going to happen is it's going to have a voltage drop across the BJT. Yeah, just like a resistor or something. Actually, Kirchhoff's voltage law for a series circuit works here. So if this BJT was, to say, half open and half closed, what's going to happen is that if I had 10 volts here, my VCC, I would have 5 volts dropping across this and 5 volts dropping across this. So what's going to happen is that I'm going to have 5 volts out here. It'll be interesting. So if I study the voltage potential right here, it's going to be 5 volts. So BJT as an amplifier gives us the ability, as a switch as well, but more so as an amplifier, gives the ability to change the voltage output depending on the current going through. And actually, I change the current going through by changing the voltage going in. So essentially, I'm taking a changing voltage going in. Right here, I've got a picture of a varying voltage. Of a varying voltage going in, which creates a varying voltage going out. That's a higher value. So if this was 5 volts, and this was 20 volts, as I change this in between 0 and 5, this would change in between 20 and 0. Now, the reason I said 0 and 5 and 20 and 0 is because they do it in an opposite way. Like I said, I'm just talking about theory here, and I need to talk about this theory before we move on. There's some math here. You guys can figure that out. Sorry. What I want to say is this. If I put 0 volts here, there's no current. This BJT is wide open. Wide open. What's the voltage at the VCC? I mean, the VCC is, let's say the VCC is 10 volts. Okay, sorry, what's the voltage of the VCC? It's 10 volts. What's the voltage V out? Again, I've got 0 volts here. There's 0 current going through here. This is a wide open switch. If I study the voltage at V out, it'll be equal to VCC. So if this is 0 volts, this is 10. If this is 5 volts, let's just say I needed exactly 5 volts here, and I chose a resistor here. I chose a specific resistor there so that when I put 5 volts here, the current going through here was fully saturated, right? So it's a fully closed switch. Exactly when if I put 5.9, that switch wouldn't be closed all the way. That BJT wouldn't be fully closed. It would be almost closed. There's just a little bit of a gap there, right? If I put 4.9. But if I put 5, boom, it's closed. So I'm going to design my circuit. I'm going to put a resistor there at the base so that the current going through at, say, the maximum voltage coming in, which is, say, 5 volts, that current is going to just saturate that. So I'll have to do some math to make sure I do that just right. I'm just going to saturate that. And when I do that, the voltage here is going to be 0. So if I put this up to 5 volts, this thing is fully closed. So what's the voltage drop across a closed switch? Well, 0. Now, you know I'm lying to you because it's like 0.2 volts, anywhere from 0.1 to 0.2223 volts. Some are small, but if we're dealing with 10 volts, 0.2 volts is nothing, right? So it's small. So I can use this actually for a sensor circuit. So if I had a certain variable changing voltage coming in, or not even not an AC, but just like a varying voltage coming in for whatever, I was like this goes down, whatever, right? So that would make a varying voltage going out. It was at a higher value, but inverse to the ups and downs. When the input voltage goes up, the output voltage goes down. And when the input voltage goes down, the output voltage goes up. They're inverse. They're just opposite to each other. But it's an amplification effect, which is really cool. So that's a theory. That's the big theory. So essentially with an amplifier, there are two things that we're going to do. One is we're going to have a varying voltage coming in, which is going to control the current through a load, or it's going to control the output. And that output I can stick into another control circuit to control something else. So yeah, and I can use this to calibrate to create a really accurate sensor, which is really cool. So here's an example of a sensor. So I'm taking a temperature sensor. Ultimately, this is a temperature transducer. What it does is it's a thermistor, right? If the temperature changes, if the environment that thing is, temperature changes, its resistance changes. Okay, so I've got a varying resistance right here, and I've got an adjustable resistor here. And what I'm going to do is I'm going to, depending on what this value is at its maximum and what this value is at its minimum, I can then adjust this so that the voltage here, this is just a voltage divider, the voltage here is going to have a range. It's going to have a minimum value and a maximum value, right? Depending on the temperature. So if the temperature changes, the voltage here is going to change. This is just a voltage divider, right? There's a resistor on top and a resistor on the bottom, and what's the value in the middle? Well, you have to do the math there with the voltage divider formula. It's not a complicated formula, but if I take that, I can calculate the voltage here, but I can see that that voltage will be changing because this value of this resistance of this thermistor is changing. So therefore, I'm going to get a changing voltage here. And as we said earlier, if I have a changing voltage going into the base, and if it's varying, my current running through my BJT will change. So I can then control a motor or something. Or I could just put a V out here and I could get a varying voltage out. I could amplify that. Now, I have to tune that circuit. I have to make sure that I choose the right base resistor. I'm all over the place. I don't know where it just happened. Hold on a second. Let me just find that. I have to choose the right base resistor here. I have to choose this correct base resistor, this resistor here. It's a lot of math here. It's like, it's not easy to do, wrap your head around. So I've got some examples here where I'm going to put a force transducer here. So this is really cool. This is actually a really cool thing. So you can take this thing and you can press on it and it changes the value of its resistance. If you press on it, it's a force transducer. So that is going to change varying voltage here at this point right there, at this point right there. It's going to change the voltage. So that voltage is going to change, which is going to change the current. It's going to change the current going through here. So how do I tune all of this? Well, there's math here and an example here. I'm sorry, I'm jumping all over the place. So this is just me going through the math. And this is the BJT itself. It's good to know the BJT because you're going to have this gain. It's going to have a maximum and a minimum depending on the current going through it. Yeah, it's really crazy. You're going to learn that. Or actually, that's what this study is all about, the fact that the gain changes and it goes all over the place when you use a BJT. So there's just more examples here, more examples. Go over these examples, wrap your head around this stuff. This is really cool. This is actually a research project that I did with students at Humber, where we built this really cool automated, called an E-ankle. So what was going on here was that we needed to know the angle. And what we did was we had this varying voltage because we put a potentiometer on here. And as this angle moved, the potentiometer moved, which changed the value of the voltage. And then we took the voltage going out and we put that into a microprocessor and we're able to actually make some changes. I mean, do some actual coding and programming and stuff. So that's it, guys. That's it. So there you go. That's everything you need to know about BJT as an amplifier. You guys, like, that's it. That's just the theory. Now what you need to do is you need to watch these videos here. This video, which is 45 minutes, and is me going over the examples that are very similar to what I just showed you. And then this is just me doing another example and walking actually through the data sheet itself, using the data sheet. And you guys need to know how to use the data sheet. It's a big deal. We're going to be looking at the data sheets for the lab. So that's it. So I've covered everything you need to know. Okay, bye.